All right, so today I want to explain another viewpoint on mirrors of curves, which involves trying to do Landau-Ginzburg theory directly on the critical locus of a mirror superpotential, or forgetting completely, in fact, about the Landau-Ginzburg mirror and the superpotential and so on. This is going to be a trivalent configuration of Riemann surfaces. And in practice, this would be mostly just complex lines and P1s. So you could develop a theory for other things as well. So this is joint work in progress with Sasha Efimov and Ludmila Kezarkov. So to recall the context, previously we've decided that if we have a Riemann surface, then it has a mirror which is a three-dimensional Landau-Ginzburg model. For example, for the pair of pens, which is still going to be my running example, you get C cubed with minus Z1, Z2, Z3, and the critical locus of that is just the union of the coordinate axes in C cubed. But in general, there's other examples. For example, if I take one punctured torus, say viewed, for example, as a hypersurface, take a cubic in P2 but delete one of the lines or something like that. So in C squared, really, this is an affine elliptic curve, affine cubic. Then the mirror would be some Landau-Ginzburg model. I don't even want to draw it, to write it, but the critical locus will end up looking like, in fact, this kind of thing with P1 union a copy of C meeting in a triple point. And if I have, say, a genus 2 curve, so at this point, it's a visible line. If I have a genus 2 curve, or in general genus G, then the mirror will be, in general, for a closed curve, it's going to be a configuration of P1s. There's going to be 3G minus 3 P1s meeting in 2G minus 2 triple points. Okay, so, and then, so far, last time we were discussing how coherent sheaves on these curves correspond to certain Lagrangians in the Landau-Ginzburg model, and I expressed the wish that one should be able to view these Lagrangians as being thimbles built from something in the critical locus. And I don't know how to make this rigorous, but for example, I would expect that the structure sheaf of a pair of pens should correspond to building a thimble out of this graph, which consists of the real positive axes inside each component. And in general, line bundles are going to correspond to graphs which run through every component and have one leg coming out into each component at each node. And so, for example, this might be a line bundle on this curve. And meanwhile, we did see also that skyscraper sheaves of points, let's try to use green for those, should correspond, I mean, these ones actually do correspond to thimbles built out of circles contained inside these components. So these things are like skyscraper sheaves of points. Okay. So to turn these, to turn the thimble on this into an object of a Fukaya category of a Landau-Ginzburg model, you need to worry about equipping it with a bounding cochain because this bounds disks. So the plan for today is to ignore the whole three-dimensional geometry and just restart from a blank slate on these pictures and try to do a version of Floer theory that does what it needs to do. But of course I want to start from, not completely in a vacuum, but from things that make sense given the context. So maybe as a place to start, Okay, so the goal, again, is to generalize usual or wrapped Floer theory with the version that allows for non-exact Lagrangians and local systems and Novikov coefficients to trivalent configurations of surfaces. And again, this is a very ad hoc construction in that I'm not going to claim that this is like, a deep insight about geometry of singular spaces, but rather of these spaces as they arise in the context of critical loci of mirrors. Okay. So as a starting point, one needs to recall basic features of wrapped Floer cosmology on the cylinder, because that's where it all starts from. So if I'm dealing with wrapped Floer homology on the cylinder, the most interesting Lagrangian to look at is a straight line arc that goes all the way through L0. And remember, in wrapped Floer theory, I'm supposed to push off L0 by some wrapping Hamiltonian that grows fast enough in the ends. Okay, and so I will find, so this is like L0 pushed off by some amount of time t, and then I will find eventually that the wrapped Floer complex of L0 with itself, as a vector space, has an infinite series of generators, but as a ring, it corresponds to a Laurent polynomial algebra in one variable. And so two features I want to draw your attention to are what products look like and what evaluations of functions look like in this. So if I want to multiply, so I should probably draw this here. If I want to do a product on this, I need 3 copies of my Lagrangian, more and more wrapped. So I will draw a version of this that's even more wrapped. Okay. And eventually I will find that operations such as x to the I times x to the j equals x to the I plus j correspond to holomorphic triangles with boundaries on, the notation I have here is successively perturbed copies of my Lagrangian, where in fact the inputs are at the two ends of the Lagrangian. And if I want to try to draw things schematically, the trajectory evolves towards the output, which is here in the middle. Okay. The output of these triangles is always in the middle compared to the others. The other thing I can do is I can evaluate that point. So how do I evaluate at a point? Well, I need to test L0 against, sorry Barry for making you do things. I need to test against the mirror of a point, so L sub p will be a circle going around the cylinder with a local system. Okay, so it doesn't work. So corresponds to a point where the valuation is equal to the amount of symplectic area between some reference position and this circle, and holonomy times t to the area, there's a local system on this. So the holonomy of that local system times t to the area will be exactly the coordinate of the point that we're at, or its inverse. And so now if you try to evaluate, maybe I should draw it here first. If I try to evaluate, say, x at the point P, that corresponds to a triangle with boundary on L0, L0, and LP. And I will see something that starts from x and gets wider and wider. And the fact that it's x and not something else is that by the time I get to the point P, to LP, this edge of the triangle goes once around. if I started at x squared, I would have something that has local degree 2, double covers the cylinder around here. So this is going to be important for understanding what happens later. So this is things like these. Okay. So if I take x to the k, and then I take the evaluation map, this corresponds to a triangle theory with boundaries on L0, L0t, and Lp, which this edge, this is x to the k, then this edge covers Lp k times. This is for positive k, negative k is the other way around. Okay? So these are features that let you kind of decode, when you see a holomorphic disk, what function it corresponds to, and evaluation at what point, or multiplication, and so on. So the idea is to imitate this on trivalent graphs, knowing what we need to know about the pair of pants as well. So let's try to redo this on the mirror of the pants. Okay, so we have the union of 3 copies of C. And so let's start with, now L0 will be the union of 3 copies of the real positive axis. Okay, so it will be here, here, and here. And it's pretty clear on general, so my goal is, of course, there will have to be some weirdness at this point, because this is not the usual world. But I would like to believe that away from this point, everything should be as usual. So in particular, this means to intersect L0 with itself, I should push it off by some wrapping. Okay, so I will do some positive wrapping. Whoops. I'm having a technical issue with too many views. Okay. So positive direction, this one. Okay, so I will have L0t, which will be a push-off by a Hamiltonian that grows in every cylindrical end. That's the wrapping part of the story. If I were on a union of p1s, I would probably not need to do that, but I would still probably want to perturb things a little bit at the ends to achieve transversality, whatever that does for me here, because after all, this is still a big mystery. Yes?
So your all the structure is just this abstract graph consisting of 3 rays meeting a point. You don't have any direction.
There is a direction. Right now I'm still trying to kind of get you into the structure that will be there. But essentially, yes, that's right. So at each point, we will just, for technical purposes, fix a direction, and we'll declare the objects to be graphs that are asymptotic to that particular direction. And when we perturb, we push off a little bit from that direction. That's right. I believe that that's not necessary, but it kind of made my life much easier when I gave up trying to do it otherwise.
Is that direction that's at the singular point, you mean?
Yes, at the singular point, that's right. At the singular point, you want...
At the singular point, you have a direction.
On each component, there's a direction that I want to call R plus or something like that, and this is the direction I will come in from.
If you and I had chosen different directions, how would we relate them?
That's a good question. That will be clearer once I tell you what the mirror of a dent twist is. I mean, essentially, once you wrap all around, something has changed. Before that, I mean, they're all equivalent, but they're non-canonically equivalent until you choose which way you want to go from one to the other. There's other things that will be non-canonical, so don't worry.
Can I also ask, maybe this is too early, maybe you're not, but what's the symplectic form? I mean, this is symplectic geometry.
Yes, so this is just have an area form, which in the non-compact components is, say, the standard area form of C or anything of infinite volume, cylindrical at infinity. And on the compact components, it will be a finite area form on P1.
So you're not using the shifted symplectic structure.
No.
This is a critical locus.
No, I don't know how to do that. I'm sorry, I'm not derived. Okay. Yes.
If I try to do this in a bigger context, should I think of this as something about normal crossing singularities, or should I think of this as something No, if you take some singular
So,
non-modifiable.
so in principle, right, we would hope to be able to do this, say, for example, on the union of the codimension 2 strata of a normal crossing configuration. Right. So, for example, in C to the n, for the mirror to be n-dimensional pair of pants, I would expect to see an n-dimensional configuration consisting of all the n-coordinate planes in Cn plus 2. I have no idea how one would do that in practice. Okay.
Because they seem kind of like, symbols or
Look,
something like
no.
that.
Okay.
No, it's not like that.
No. No. I don't, I mean, anyway, it's possible, but I am not going to go there because I just, I barely understand this case to begin with. I'm not ready to go to higher dimension. I mean, yes, there should be a higher dimensional story, but right now I have no idea what it is.
I didn't mean to.
Yeah, okay. That's okay. Okay. So, all right. So, okay, that's great. And so now we want to consider this Bragg-Fleur homology, and we keep in mind that this is meant really to represent what happens in the total space in the initial phase, in the C cubed minus Z1, Z2, Z3. So we use that to guide our intuition. So in particular, we want the outcome, we do want the Fleur homology of this thing should correspond to functions, the range of functions on the pair of lines. Okay, so what do we see immediately on the picture? So we see that the Bragg-Fleur complex of L0 and 0 has three infinite series of generators in the legs, in the cylindrical ends. Right, so I have a generator here and another one here and so on, and gosh, I didn't wrap fast enough, but you know what I mean. Here, here, and so on. Okay, and then there's question mark at the node. Okay. So what can you tell about the things in the legs? Well, the first observation is if you try to multiply together the things in the legs. So for that you need yet another copy that's wrapped faster. But see that inside the legs, you expect things to work just like in the cylinder, at least on one side of the cylinder. So when you look only at positive powers of your Laurent variable. So in the legs, these should correspond to first order, I'll explain what that means, successive powers of some coordinate. So the intuition from the case of a cylinder is that, say, this leg corresponds to this puncture of a pair of pants, that I should have a local coordinate near this point, and that these generators should correspond to successive powers of the inverse of that coordinate. And that would be consistent with the idea that when I multiply now, so if I have yet another copy, and then I try to build these triangles involving 3 copies of my Lagrangian, it will look exactly like this picture inside the leg. And those are the only holomorphic curves I can see that live purely in the neighborhood of infinity here. Now, because there's a big mystery here, I cannot exclude the possibility that some curve would start and cover everything and do something crazy and eventually come back or go somewhere else. In practice, for the local picture at the endpoints, so when you have a generator that lives in a leg, and it's an input into a Fleur operation, then the local picture has your holomorphic disk going either this way or that way. And so if it doesn't stay in this region, it has to go to the left from both of them and somehow find some way to close itself up. This would have much larger areas, so it would contribute much less. I cannot think of a smart thing to do with those, so I will postulate that in fact, this is on the nose successive powers of a variable. And it turns out this is a consistent choice, so I'm not going to worry more about it. Okay, and now, sorry, just a moment. And if you try to evaluate at points, so now again, if you evaluate at points which are in the same leg, okay, so these correspond to skyscraper sheaves of points in that small coordinate chart, then I would also want to see the same kind of picture that's over here, that the evaluation at a point corresponds to indeed some power of a coordinate that gives the position of that point. coordinate in what coordinate system? That's the big question. If that's what you're going to ask about, I will talk about that. Otherwise, what was your...
Oh, so, I mean, you have x1, so you do this, you have a local coordinate, say x1.
Exactly, I will need to have some local coordinates at each of the punctures. I'm going to go to that. That's going to be the next 10 minutes at least, yes.
So, but we know how they transform and they will cover the whole field.
That's the idea, yes.
Okay.
But you need to choose them. Okay, so yes, yeah. Yes, I think you're...
Sorry, I missed. What's this thing? It's a node or question marks?
Oh, sorry, yes, so I need to tell you. So after the fact, once you've started doing calculations with this and so on, you will find out that what you need is just, there's one generator at the node, which corresponds to this intersection that you see. Because this was not preordained, and actually a saner model that kind of starts from first principles of symplectic field theory or things like that would say, no, you have to cut this out and then put here a Lagrangian contact homology and then wrap, counter wrap, and you get these big infinite dimensional models. The claim that's being made now is you can forget about all that theory and just go ahead with what feels right and put one intersection here, and it will actually work. Okay? Of course, right now this is just as a vector space. We need to talk about how we'll define Floer operations on that.
When you say work, you mean it will produce the right mirror?
Yes.
Symmetry.
Yes.
But if you had something higher dimensional and a different singularity there?
I don't know. Again, I told you I don't know what happens in higher dimension. Okay. I believe something can be done for things that look like locally toric, whatever. For things that look like codimension 2 strata of locally toroidal configurations or something like that, I believe something exists. I haven't thought about what exists. I'm assuming you would start doing intersection theory inside the lower dimensional strata as you encounter them. But, yes, I think by the time we get to the end, if you're higher dimensional minded, you will see how this would work conceptually. But the details kind of have not been checked at all. So, okay. All right. So, okay. So at this point, Melissa has realized, and probably several others have realized, and anyway, that we need more choices to actually specify what's happening. Oh, all the green pens have migrated here. Okay. So, recall that the manner in which LP determines an object of the Fukaya category of a three-dimensional Landau-Ginzburg model now depends on the construction of a bounding cochain, a recipe for choosing one. And so this is what's called framing data in the work of Cannizzo, Melissa Liu, and collaborators and others in this direction. Okay, so at a high level here, this amounts to a choice of a local coordinate near the puncture of the pens. Okay, so when x1, say for example, let's look again. I'm going to move away from this embedded version of the pants at some point because we want to think of it more abstractly. But if I think again of my pants as being this hypersurface in C star squared, as in the previous talks, there's an end of this, which is where x1 goes to 0, then natural choices of coordinates could be x1, that's the most obvious one you can choose, but one that's equally good is negative x1 over x2, also known as x1 over 1 plus x1. And there's others that I feel are less natural, but maybe Melissa has. Anyway, in principle, there's many of them. These ones are my two favorite ones. And observe, you can't really decide between the two, because in fact, the valuations of these coordinates, remember, everything is in the Novikov field, so there's a valuation, and because valuation of x1 is positive, dividing by 1 plus x1 does not change the valuation nor the leading order term. This is all in the higher order corrections. Okay. And so this actually should correspond to the area enclosed. The dictionary between, what I mean by that is, it's supposed to draw a circle inside one of these complex planes and equip it with a local system, and the amount of area bounded by that circle corresponds to the valuation of a local coordinate. So as the circle pushes more and more out towards infinity, you actually go closer and closer to the puncture. Okay. So that choice will have to be baked in, because that's the price for forgetting about the ambient space and this issue of bounding cochains and all that.
What happens if I push the circle up to the node?
So if you try to go all the way into the node, then in principle you would get the mirrors of the points whose valuation is 0, and we don't know how to access those directly. So what we'll do instead is we'll focus on mirrors to line bundles, and we'll use evaluation at points of non-zero valuation to figure out, what to do. But the objects that correspond to skyscrapers of points of valuation 0, we just, don't try to define a Lagrangian directly. I mean, you can eventually recover them as mapping cones between line bundles anyway. Mm-hmm. Yes.
The framing will define a superpotential spans, and there is a unique critical point which skyscraper should go to.
Mm-hmm. Yes. So it's the mechanics of how choices of framings determine coordinates and so on. Yes. I just don't want to go into that anyway. I mean, but that's correct. I mean, one can dig into this, but at the high level end of things, all you find is that the objects that you want to think of as being a circle enclosing a certain area with a given local system correspond to a point in which some coordinate determined by some choice you've made in advance is equal to t to the area times coordinate.
Can you just say one more time, what was the choice we made?
Just a moment. So, sorry, not x1 actually, whatever coordinate you choose. So the choice I'm making is of a local coordinate, actually a global coordinate if you want, on the pair of pants.
On the mirror to this.
Yes, so on the mirror to this, so really on a pair of pants, always on a pair of pants. Okay, that a local coordinate near a puncture of a pair of pants. Okay, don't worry, I will go through all of this again once I get to the actual definition. This is still the motivating the construction thing.
Do you near each puncture you choose one?
Wait. Okay. It will come. All right. So, one last thing I need to tell you. Okay. So one thing to check is that 1 and all the powers of the inverses of local coordinates at the 3 punctures. So I'm still on the pair of pants, but later on there will be lots of punctures in lots of pairs of pants. Form an additive basis of functions on the pair of pants seen as P1 minus 3 points. Okay, and that's basically partial fractions. Okay, so and it doesn't matter how the respective coordinates are chosen. This just works in general. Okay, so all right. But so the other thing that should still be bothering us is that something, it can't be this simple. Okay, so why can't it be this simple? It's because if I take a function which is a power of a local coordinate at some puncture, okay, so it's somewhere here, it's maybe a generator here, and then I want to evaluate it at a point which is in fact not in this leg that I already know how to do, but in a different leg. Well, certainly, a holomorphic function on a pair of pants is nowhere identically 0. I mean, unless it was, so there have to be holomorphic disks that start like this, and if this was like the cave power of the generator in this way, then by the time you get to the origin, you're covering basically K21, if this is next to the K. And then somehow your disk needs to find a way to escape into this leg and eventually end here in a certain way. So there needs to be, you need to have some, what I will call propagation of Floer trajectories through the vertices. And in fact, just consistency of what you're doing on the pair of pants dictates the rules for propagation, because what multiplicity you use to count this kind of trajectory going to something here which has certain covering degree on this side is dictated by the power series expansion of this function in the local coordinate at that puncture. So that's what we're going to do. We're just going to use power series expansions of powers of a coordinate in terms of the other coordinate to decide what kinds of propagations happen. Okay, so now the ingredients are in place, and I can actually start from scratch giving you the definition. And hopefully details will be clearer with the definition. Okay. So, data that we need before we can talk about a Fukaya category. So we have something which is, configuration of Riemann surfaces. Let's say that there are many P1s and A1s. It's trivalent. Okay, I don't know what I'm doing. I'm just going to draw some random configuration. Okay. So one thing we need to have, basically symplectic forms on all of these. But if you want about the relevant data, the symplectic area of the P1s. If you want more refined data, you could have bulk deformations on top of that if you need to, which means essentially T to the area gets deformed instead to an arbitrary element of a numerical field. Okay, and then the areas, I guess, of the P1s. And then we need to choose what I will call chart data at each node. Okay, so whenever I have a node in this configuration, I will equip it with the data of three quantities I will call, say P1, P2, P3. There's going to be labels in general for all of these things, which should correspond to local coordinates, or rather, sorry, I'm going to use inverses of local coordinates on a pair of pants, P1 minus 0, minus 1, infinity. Okay? And so, near the punctures. So what they should be is that, so when I said local coordinates, I actually mean global coordinates, but with a condition on what they do. So P1, P2, and P3 should be functions on the pair of pants. So if I extend them as meromorphic functions on all of P1 with a single pole at the respective puncture. Because I haven't decided in advance which one, it doesn't really matter which one of these I call which of 0, minus 1, infinity. Any 3 points on P1 are the same. So it's just I like these 3 points best because these are the ones that you can define without any coefficients. Okay, and and no other poles. Okay, so in fact they're just degree 1 rational fractions. So there's many choices, but I think the preferred choices from an aesthetic perspective, in terms of being also defined over any field of coefficients, as far as I know, and without subtraction, once you flip your sign correctly, are if they take values minus 1 and 0 at the other punctures. So in fact, I claim my favorite local coordinates are things that they are maps from P1 minus these 3 points to itself, that permute the 3 punctures in certain ways. So at infinity, my favorite coordinates are either z or minus z plus 1, depending on whether I want to make it vanish at 0 or at minus 1. At 0, the favorite coordinates I have are minus z plus 1 over z, or more straightforward 1 over z. And at minus 1, minus 1 over z plus 1, and the other choice is minus z. There's a sign that's wrong somewhere. This one looks good. I can't tell.
So it's 1z and minus z minus 1, you just take the ratios. Is that how you go?
Yes, something like that, yes. So anyway, so these are the, and in some sense, yeah, okay, so these are my favorite choices of local coordinates. Okay.
So why does it have to have no other poles?
Because that's how I like it best. I don't think it actually matters, but
Well, you would have many more choices, right?
I would have many more choices, yes.
Okay.
I believe that the natural choices do not have other poles, but yeah, okay, Melissa is about to contradict me.
That's fun.
Okay. Anyway, I hope that Melissa at least agrees that these are not bad choices. They are among the natural choices, and maybe there's a much larger set of choices. I haven't thought about what happens with others. Yes, okay.
Do you have 2 options or 8 options in your preferred choices?
Depends how.
First column or first column and second column? Or
The very nicest ones go by column, because then the product of the 3 is 1, and there's like some relation among them. In practice, it's much easier to mix and match, because when 2 of them are inverse of each other, then some simplification happens in the propagation rules, and that makes your head explode less quickly. So, yeah, the aesthetics is best when you go by column. The examples I will take do not go by column, because calculation is easier if you do. Okay. All right, so having said that, okay, so what is the B-side interpretation? What is the mirror interpretation? So remember that mirror symmetry happens near maximal degenerations. And so near the maximal degeneration, your favorite, let's take the example of a genus 2 curve, just for concreteness for now. Anyway, so your curve is going to be a smoothing of subnodal degeneration. A maximal nodal degeneration of a compact genus G surface is just given by a decomposition into pairs of pants. So if you choose a pair of pants decompositions, then that determines a way to degenerate to a maximally nodal configuration, which is a union of P1s with 3 marked points each. Attached together at nodes, pairwise. And so in some sense, the configuration will end up with is dual to this, in that you replace each P1 by a point and each point by a P1. Okay? So, and for this, what we do is we glue P1s together at, let's say, minus 1, 0, infinity. You don't have to, using, for each node, a smoothing model of the form, it's called some local coordinates y and y prime equals t to the a, which is some Novikov variable, and this will be actually the area of the P1 in the mirror. Okay, so each node here will correspond to a P1 in the mirror. This is what I see here. And the area of that P1 will tell me how quickly over the non-Archimedean field I want to smooth the node there. But to smooth that node in such an explicit way, I need to have chosen local coordinates. And exactly what smoothing I get depends on the choice of local coordinates. Okay. So maybe actually a slightly more refined, less stable way of thinking about it, but that will allow us to kind of understand the geometry of what's happening inside here, is to take an unstable model where we add an extra P1 component inside each node. So what is slightly more convenient when you try to work with these things, you start with actually an extra P1. You insert an extra P1 inside each node. Okay. That one has coordinates, let's say x, and so x is coordinate going this way, and x prime is a coordinate going that way, and x prime are going to be almost inverses to each other. Well, yeah, actually, let's just make them inverse to each other. Let's normalize this way. And then here I have my local coordinates y prime and y. I think I'm backwards. Yes, y prime and y. And then what I need to do is I glue P1 near 0 to the pants, to one side of the pants, by x times y prime equals t to the a over 2, and I glue the point at infinity to the other pants, to pants prime and this one to pants, by x prime times y equals t to the a over 2. So what this does, this is like an analytic way of explaining, but basically if you were to replace these by cylinders of finite modulus, then what you're making sure of is that you insert a cylinder of modulus A inside here. This kind of enforces the area A. And the advantage of thinking about it this way is that now you have access to the points inside that P1. And the points inside that P1 are exactly what these Lagrangians in the legs will correspond to. Right? So if I want to think of the skyscraper sheaves that I can see, I cannot see any of the skyscraper sheaves that are sunk inside the pairs of pants. I can see the skyscraper sheaves that live inside the P1s. And these correspond to points that are actually inside this part of the Riemann surface. Okay?
What about the skyscraper sheaves at the other points?
I do not have a direct mirror to them. Well, of course, sorry. So, once you have something like this, once you do the gluing, you know how to express the position of that point in that coordinate. And then you can ask, does there exist a circle on that P1 that bounds the right amount of area? But if you're far enough in, then the area you want to enclose would be negative, and you'd rather not do that. Sorry, no, except if you do that right, actually, there's no area left. This is only the points of valuation 0 in the Archimedean sense that are missing. So I have to correct what I was going to say. Okay. And so the choice of chart data in the A model reflects the fact that this kind of construction is not canonical until you have chosen local coordinates. That's basically what's happening. All right. So having fixed the data, now we need to talk about objects of a category and about morphisms, and then about differentials. Okay. So the objects. And so I'm going to say offline bundle type are going to be trivalent graphs with one arc on each component. I have to use every component. And fixed tangent direction at the nodes. Plus local systems on the arcs trivialized at the nodes. So I'm basically trivializing everything, the direction of the thing and the local systems and so on at the nodes, because that makes it much easier to talk about what is the holonomy around the loop and what is the area enclosed and things like that I suspect this is just like a lazy way of dealing with it. So for example, on the mirror of the genus 2 curve, I might draw something like and this would be morally a line bundle on a genus 2 curve, which is assembled from the pictures here by having something that wants to have degree -2 here. I think I put 2 twists, degree 1 here and degree 0 here. So in fact, this will be a line bundle of degree 1, I believe, on a genus 2 curve. Or in the, maybe slightly easier, in the non-compact case, then of course there's not really meant to be a notion of degree. Okay. All right. So a small mystery, by the way, which is not very easy to parse out, is if I start inserting a Dehn twist here, then I get something that looks like it wants to become a line bundle of degree 1. I'm twisting by O of P. In fact, the intuition that you have that performing a Dehn twist here is mirrored to tensoring by the defining line bundle of a point, which is the point corresponding to a skyscraper that you twist about, remains valid. What is not easy to see here is why this operation is in fact isomorphic to identity on an open curve. I mean, you can calculate and then it works, but there's not an easy way to see it.
You do not allow like these simple nodes? Yes, where just 2 components come together?
No, that's not allowed. And the reason is this wouldn't be, if you start thinking again about the 3-dimensional ambient mirror, this would be an unbalanced configuration to start building a tropical Lagrangian from. So when you use a node, you need to use all the legs. In principle, a higher rank bundle would be a system of things which runs as many times as the rank into each node. I have no idea how to deal with that, so I'm not going to worry about it.
And higher genus components? No.
If you had higher, these do not occur in our setup. You can do the definition with higher genus components. The definitions just work fine if you have higher genus components. I don't know what the outcome is.
So does it give some mirror to no maximal degeneration? So, like, what happens if I take a no maximal degeneration of the curve? What should be the mirror to?
If you take a non-maximal degeneration, so if you take a non-maximal degeneration, then the mirror Landau-Ginzburg model will not be smooth, and then the critical locus will have collapsed components, will have some stackiness, so I don't know how to deal with that. So these are just mirrors of curves near the maximal degeneration. But you can do every maximal degeneration. That's already a good starting point. I mean, sorry, something else I should have said. Okay, there's an obvious generalization. If you do a degeneration that's still into a union of P1s with marked points, you could just try to do the same thing with a higher valency graph and local coordinates at all the punctures. And I suspect it would work directly. That case would probably work directly, just by imitation. Yes?
So what happens to like between 0 line bundles which are not trivial?
Well, that's going to come. So one quick thing to point out, okay, so since Melissa's asking, so you can see, the degree of a line bundle is basically the total number of twists that you make. And if you want to know where you are in the Jacobian, the idea is, you have non-Hamiltonian deformations of this by moving this arc to sweep some area. Or you can change the holonomy of a local system along this arc. Remember, we picked trivializations here and here. And essentially, you can work out to first order how you are actually moving inside the Picard variety. One way to think about this is if you just start from something that was trivial, O, and then you twist at different points inside here. You can do the Dehn twist here or here or here. These will form a continuous family of objects, but there's an amount of area swept between them. And so you can actually start playing games and understand things like Abel-Jacobi maps and theta divisors and so on. It quickly gets very hard because the formulas are just, once we talk about calculations, it's very hard.
Can you check the topology as well?
Yes. All the basic calculations about Riemann-Roch and so on work out and so on. Yes, the topology works well. But the closest I came to ever seeing a theta divisor was the case of a once-nodal genus 2 curve. There you can actually see it. The smooth genus 2 curve, I can't do the calculation. I mean, it starts having the right kinds of expressions, but I can't do the calculation. But since we have an HMS statement, you know at the end of the day that yes, it works. Okay? So eventually it all follows from homological mirror symmetry. So initially you want to do calculations to convince yourself that you can see features, and you can see some features. Okay. So, so the other thing to say is, the number of parameters now, at least the dimension of the Jacobian, right, is, these things, they are graphs of genus 2. So in fact, the only thing that really matters is the area swept by the loops of this graph. There's 2 deformation parameters. If you change the holonomy here by some amount of sweep area here, but you sweep the same amount of area in the others, then actually nothing happens. Okay, so to define from AB, we push the legs of A at the vertices slightly counterclockwise, and we wrap positively in any non-compact, in any affine components. Or cylindrical ends if you fantasize about higher genus species and so on. And of course you can do a version with stops at infinity as well, where you stop the wrapping. That actually works very well too. I'm just not going to go there to keep things short. And then we declare that we have 1°0 generator at each vertex, plus generators at all other intersections as usual. Okay, so for example, if I look at this example here, which is mirrored to a once punctured elliptic curve, if I take this thing, which is O, and I try perturbing it a little bit, so I push a little bit counterclockwise, so I believe this goes a little bit like that, and here I need to go a little bit like that, and of course to reconnect, I need to have an intersection here. And in this end, I think it's like that. Okay. You'll have an infinite series of generators. Okay. So here you'll have an infinite family of generators in degree 0. Here you have one in degree 0. And here you have somebody in degree 1. Perhaps more interesting. Right, and so, of course, this is not yet, there's going to be a differential, you can see, because if you look at the cohomology of O on a once punctured elliptic curve, in fact, there's no H1, and there's an infinite dimensional H0. So we'll have to get back to that once we can tell about the differential. Let me also look at O, say, on a genus G curve. So if I look at O on a, say, genus 2 curve, so I take this graph, and I push it slightly, so I realized it more than I wanted. So I push things slightly counterclockwise. That's going to go like this, I think. I will find that there's degree 0 generators at the nodes and degree 1 generators inside the legs. Okay? And so you can calculate at least the Euler characteristic of this complex, and you will find 2 minus 3 equals minus 1, which is 1 minus g. And if you start changing the degree of your bundle, you see that the Euler characteristic will follow the Riemann-Roch formula. Okay? So, in general, you find indeed that on a Riemann surface, in a closed Riemann surface, Euler characteristic of a Helm space from L0 to L corresponding to some line bundle will be indeed 1 minus G plus the degree, plus the number of twists, okay, which is kind of comforting. Okay, so let's talk a bit about the interpretation on the mirror. So the idea that I picked, that I kind of standardized things at the nodes, that I have something with fixed directions and fixed trivialized local systems corresponds to having O on each path in my decomposition, okay, in this picture. And meanwhile, now when I see a P1 and I have something with K twists, this corresponds to O of K on P1, but with distinguished trivializations. At 0 and infinity. And how these trivializations relate to each other has to do with how much area exactly, where do you put the twists, and what is the holonomy of the local system from here to here. And then, so you imagine now that every line bundle, well, at least most, well, I think every line bundle, on these surfaces obtained by smoothing these nodal configurations can be indeed obtained by gluing together copies of O on the pants and copies of O of K's on these with choices of isomorphisms at all of the nodes. And of course, this way of building it is non-unique, which is why we have different Lagrangians that can represent the same object. Okay. And so you can check indeed now that, if you look at the hums, this hum corresponds to the constant function. So this is probably not very readable, so let's try again. And so the degree 0 generator here corresponds to the constant function on the path, which is the only global section of O in here. And in here, if I intersect O of K with O, I will see K minus 1 interior generators. So that's of for K positive, which correspond to the sections of O of K which vanish at 0 and infinity. Okay, or maybe, yeah. And so, and then of course when you are, in general this is like the cohomology of O of K twisted by negative of the divisors at 0 and infinity, because you exclude the ends. And what else did I want to say? Right, so, and of course if you see an affine end with an infinite sequence of generators, these are just powers of the coordinates, and these are just like the functions on that A1 piece. I didn't really have non-compact announcements. And so now, once you have that, you want to think about, of course, you cannot just take a function that's defined on one of the components and brute force extend it. Okay? But you can ask, does it have a chance of extending through? So for example, if I take, say that I have O of K inside this P1, and I take some homogeneous polynomial of degree K, which vanishes at 0 and infinity, then I can try to deform it under the smoothing to a section of a line bundle I'm building by assembling things together. Whether I will succeed or not depends on whether the Floer differential of a generator vanishes or not. Same thing here, the constant. I can take the constant function here and try to extend it. And of course, I can extend it globally by constants, but if I just take this guy by itself and I try to extend by 0, there's an obstruction. The manifestation of that is that, see here, there's these small holomorphic disks. that you see right away. So these small holomorphic disks will tell you immediately that D of this is, well, there's going to be bigger things because of propagation and all that, but there's first this plus this plus this. The obstruction to extending the constant function 1 from the pants by 0 on the adjacent legs. And so, of course, instead, if you take this plus that, if you make the constant function 1 in both pairs of pants at once, then you just extend by the constant function 1. But you cannot have a global function which is 1 here and 0 here. Okay, so the kernel of the Floer differential will be, in fact, the sum of these two. That's H0 of O. Okay. So now that we are getting oriented, I'm of course running out of time. That's fantastic. Let me at least give you the propagation rule. Okay? So the idea first, sorry, maybe I should have said that, okay, so, you know, the Floer differential, which is mu1 and mu2 and so on, count trees of holomorphic disks. So what I mean by that is if I want to look at the differential on hom AB, so I may have something that starts inside a component at some intersection of A and B. And typically what I will see happen is that because of the way things work, it will arrive into a vertex. I mean, of course, it could end there. You know, the whole polygon could be inside here, and that's completely legal, and I love that. But if that doesn't happen, my holomorphic polygon might have an output at the node. Okay? So this is maybe an input. Things go from the input to the node. At the node, it's going to be incoming with local degree. Let's call that D1. Okay? And that degree has to be at least 1 because of the local perturbations around there. There's no thin things arriving because the Lagrangians are ordered, have been pushed off in the opposite direction. And then it's allowed to choose a way to go. It can choose a leg to go into, this one or that one. It only goes into one at a time. Okay? And it goes out into another leg with degree D2, which may be greater or equal to 0. Because after all, see, these things go from here to here with thin strips, which are local degree 0. And so to find out, so this has, and eventually, you can propagate more and more, but eventually it goes to an output somewhere. Okay? And so then this counts with, of course, the product of all of the T to the areas, holonomies of the components, times the product of multiplicities. And the last thing I want to tell you is the multiplicity formula. So if I'm incoming with degree D1, again at least 1, and outgoing with degree D2 equal to 0, and remember I had these local coordinates P1 and P2, then what I want to do is the coefficient, I want to calculate the coefficient of P2 to the minus D2 in the expansion of P1 to the D1 near puncture 2. Okay, so what that means is an incoming holomorphic disk of degree D1 represents locally the D1th power of the local inverse coordinate here. This is a function on the pair of pants which has a pole of order D1 at this one. It's regular near the others, so expand it as a power series. Take its Taylor series expansion in the local coordinate at the other puncture, and the successive coefficients give you the multiplicities with which you count things. So now if you use my favorite coordinates, most of these coefficients are sometimes 0, sometimes 1, sometimes binomials. They're relatively simple combinatorial quantities. And you can calculate propagation rules. So for example, a good test here is to calculate the cohomology of O here, the ring of functions of a one punctured elliptic curve. What you will find is that this one is closed because these two strips cancel out, and things really cancel out in pairs. And that's because the constant function 1, of course, is perfectly fine. Now, if you take the next one, the first generator here, that would correspond to a function on the once punctured elliptic curve with a single pole of order 1 at the puncture. We know that doesn't exist. The proof that it doesn't exist in this language is calculate d of that. So you see something that comes in as a disk of degree 1. Then you propagate it. And because, first you might think this is hopeless, the picture is symmetric. But the choice of coordinates forces you, in fact, to have a lack of symmetry, so that indeed d of this will be some t to the area times this guy. If you take the usual coordinate choices, this disk either propagates here or propagates there, but not both. If you look at the next ones for with pole orders 2, 3, and so on, they're also not closed, but now by taking linear combinations with that one, you can actually find again that there are functions with pole orders 2, 3, 4, and so on. And then with more work, you can actually calculate the product structure and find a presentation in which you recover the Voyage transform of your elliptic curve. So that's, pretty nice. And then you can calculate anything else you want. The short answer is, HMS holds because basically it's been rigged to work, because what I'm doing here is essentially baby imitation of if I try to build holomorphic functions by analytic extension continuation across all these nodes propagating through the smoothings, what are the obstructions to that ever working? And that's essentially what the Floer differential replicates. Okay, thank you. Yes? Oh, sorry.
Just a sanity check. So how do I see from that picture that there are no constant global functions if the mirror curve has no functions?
So if I want global functions, then I need to have, okay, so on a compact curve, it looks like this, possibly bigger graphs.
Yeah.
And so the degree 0 generators for an instance of O are just at the vertices. In the legs, you see always degree 1. The leading order term of what happens is that d of this, there's a thin strip that goes to here, and there's a thin strip that goes to there. Now, if I wanted to, I could try to look into bigger, because I start with a local constant function, there's no higher terms in the perturbative expansion, and it's game over, this is done. If I were instead trying to look now, a more interesting exercise you can do is twist in one leg. And now you have a degree 1 line bound on the genus 2 curve, and you can ask, when does this have a section? Okay. So the answer is you start with now this thing, and there's not this obstruction here anymore. And so now you have to actually calculate the differential as a 2x2 matrix from this two-dimensional vector space to that two-dimensional vector space. Propagation is too hard because it's indexed by the free group on 2 generators, paths in this graph. If I actually make the area of one of these P1s infinite, so a puncture here, which means now I have a mirror to a once nodal genus 2 curve, then I kill propagation through this, apart from very thin strips. So propagation now proceeds by just things running around this loop, around, and eventually possibly exiting here. But they can't propagate all around that one. So then I have, again, series indexed by z. And what you find is entries that look like theta functions of various kinds, translated and so on. And they're kind of all messed up by various areas of things in there. When you calculate the determinant, you end up with a ratio of 2 theta functions at 2 different points. And indeed, this tells you the following thing. If I have a once nodal genus 2 curve, which is formed by taking an elliptic curve and matching 2 points together, if I have a degree 1 line bundle in this elliptic curve, it always has one section. Whether that defines a section on the nodal curve is whether the values of that section at the 2 points I identify match under the chosen isomorphism. So of course I have to have a ratio of theta values matching exactly. And that's the boundary of what I can calculate explicitly by hand in here. Yes, Roman?
So, in the compact case, does it make sense to swap the roles of the two sides to consider differentiation of this trigonometry?
So what you need to do, right? Sorry. So swapping the roles of the two things, right? So you should be looking at So going back to the context, right? We had no symmetry really between a curve and this three-dimensional Landau-Ginzburg model, and we were supposed to be looking at dB sing, and we know by results of Auroux that dB sing of a Landau-Ginzburg model only depends on the formal neighborhood of the critical locus. So what you want to do is do algebraic geometry on these trivalent configurations of P1s and A1s, but viewed as being critical loci in Landau-Ginzburg models. So there's rules of, it's not coherent sheaves, it's something slightly different. But it's something manageable, it's been done before. And somehow this one is the exotic side because symplectic geometers are not good at dealing with singularities. Sorry, Sasha?
So in what form do you envision matching the kind of modular parameters for curves or E to this side? So the activity of taking sheaves depends on the point on modular space of curves.
Yes. So I mean, again, the piece of the moduli space of complex structures and curves that we see is exactly given by this. Right?
So you're taking kind of some open chart.
So I take an open chart in the non-Archimedean sense, because there are moduli of non-Archimedean curves over the Novikov field near a maximal degeneration given by these kinds of curves. And of course, I don't need to take a pure power. I can put times some this plus higher order terms using bulk deformations. So basically, it's the chart near this maximal degeneration, which of course is just so near any maximal degeneration.
There exists some map. Right?
Yes, exactly, and that map is given by whatever this gluing algorithm does. I don't want to think further about coordinates on the moduli space. I just want to say this gluing algorithm gives a local chart near that maximal degeneration.